Okay, so I am going to showcase a few of the GUI examples that are in the course repository in the subfolder called GUI examples. These are ones that we're not, for whatever reason, displaying in class. So I'm just going to show them here. So when you install them, they should show up in your apps menu. If you hover over them, you should be able to see the actual installation location on your computer. That's this blue hyperlink. If you click on them, the window should open. They should all be arranged where we can rescale them. This is under the Tools option, GUI options, and making it proportional rather than non-resizable allows us to do that. That's one of them that we're going to explore. The simplest one we have we called Kinetics GUI, and this is a really simple and not very well done GUI, but this is the very first one that anyone in my lab put together. So the idea was we could change this inlet ratio, use a slider bar to quickly see the response on the graph. And so not only do we have the plot response, but we have this theta b value, this static text is changing, indicating that ratio. Theta b is the same thing as this CB0 over CA0. And we see we have legends, and we're able to clearly see some curves. Is this amazing? No, but it demonstrated for us the utility of such a tool and the ability for us to do this with undergraduate students and myself who had not built GUIs before. And so with that one, I'm going to hover over it and open the background code briefly. So it has a figure file and an M file, and it has the code that actually runs the model. So I'm going to open up the M file. We have all the do not edit text at the beginning, the opening function. We customized and said the starting value for theta b should be 1, and we ran the plot to start with the value of theta b is equal to 1. We have a function that is how to update the plot. It needs to take the handles and the current value of theta b. It's going to run that separate model M file with a theta b value and come up with some output. And then we plotted that output on the axis that was in our window. Are there other ways to do this? Yes. You'll find that there are generally dozens of ways you can do the same thing. And so it'll be more like when I'm grading particular projects or assignments, I'll be looking at, did you accomplish the objectives? And if you came up with a creative way to do that, then that will be fine. The push buttons did not have any responses that were anticipated, but the slider that was in there did. I don't actually think that we ended up keeping any of these push buttons, but you end up with sometimes lingering blocks of text that may not have any functionality, and they might be related to buttons or objects that you put in there, components that you might have deleted, and so you might sometimes want to do some housekeeping, but it doesn't actually hurt the code to have more stuff that has no purpose. It's just bulkier. So the slider 2 is the name of the component that we used, and so we said 9 times the value, so the value is between 0 and 1, and we actually wanted it to range between 0 and 10, or between 1 and 10. Yeah, it starts at 1. If the value there is 0, then this one's value is 1, so the ratio would go from 1 to 10. And so you could do other math to be able to use the information on the slider bar, or in the slider bar you can set its min and max in the property inspector. And so I can show you briefly how that works. So if we say guide, and I want to open an existing GUI, and I do want to open this one, which it's in my C/users and all the way through here. So I'll just follow that path that I'm seeing. Documents, MATLAB, add-ons, apps, Kinetics GUI, code. All right, so I'm going to open that one just to be able to see the layout. And if I'm on this object, this slider, one slider two, if I either double click on it to open its property inspector or open the property inspector by right clicking, I can see that it has a min and a max value. Right now the min and max is 0 to 1. If you knew that you wanted it to go from 1 to 10, you could do that, and then you wouldn't have to do any algebra. There's various other things you might want it to do, and so that's how you change that particular information. Okay, so I don't need to change anything there, but note that my tags are not obvious things. Axis 7 is a very random. My student that was doing this was playing around a lot before he settled on this version. So this is not a polished, amazing version of any kind of GUI, but again, it is the first one that we got to work. So we'll move on to another example. It's a little bit more elaborate. Back to the apps menu. So that was kinetics GUI. We're going to look at CHE 3123 problem 8.8. So armed with knowing that he could program a simple kinetics problem, I asked my student to recreate a homework problem for our class, my kinetics class that's in the spring, and the students in the kinetics class are tasked with solving a complicated drug dosing problem where the first dose might not be the same as the second and following repeated doses, and they're supposed to be trying to get it above this bottom line and below this top line, and they're supposed to be trying to get the blue curve to be between those bounds. But in order to do this with the simulation software that comes with our class, they give it an initial condition, and they can run one interval or one set of the differential equation, basically one dose. They can go from 0 to the end of the first dose. But in order to do the second dose, they have to save the output from the first as a table, take all of those final concentrations, so here it's just 2 values, but then they have to put them back into their solver, start here, and manually do the next dose. They have to keep doing that and tabulate all the results in order to construct one plot. But as you can see, this starting guess is wrong. It does not create a blue curve that stays oscillating between these two barriers. And so they have to do a lot of iterations, and it's very, very tedious. So instead we made this tool that is very simple, and it uses MATLAB to add a dose at each interval that's specified, and the differential equations are quite simple. It just adds the solution to a previous interval, and it says if there's still another interval, add the new dose amount to the previous initial condition, and then it continues on and solves the differential equation as many times as it needs to for the number of doses in the time window. So it's actually pretty straightforward. You all could code that pretty straightforward based on your performance on assignment 3 in this class. So this one for the kinetics class, the students are supposed to be able to probe the significance of changing certain parameters listed here, and also on the body volume, and be able to determine the appropriate size of a first dose, a second dose, and the timing between them. The upper and lower bound are not ones that they could change for this particular problem, but they could change it for extending it to other scenarios. And so that's why there's lots of boxes here. If this was for a different purpose, we wouldn't have the user have so many options, and particularly to not know what are reasonable magnitudes. But for the purpose of that class, it's important that students can vary these different parameters. So we can put in, let's say, this time of the second dose, or let's say the size of the first dose is a little bit larger. We can see the effects of that. Well, we should be able to see the effects of that. Okay. I'm going to move directories and try running that again. Let's see. Undefined functional variable kinetics GUI. This may have something to do with the name of this particular window. Let's try running it again. That worked just fine. And let's set the size of the first dose to be 200. that's unusual. Okay, so I did get some solution answer here that this is a little bit higher. Let's say that our second dose is a bit larger, and we can get the simulation. So the first dose is not quite large enough. So we basically give it a loading dose, and this is kind of what Minu talked about the other day, a little bit in her work. But this type of thing is part of the undergraduate kinetics book as an example. And so with a few just playing around with some numbers, we can easily get a solution that satisfies fitting between this upper and lower bound for acceptable concentrations. So those are kinetics motivated examples. I'll briefly show you the heat conduction GUI. This one is 2D conduction in a square object, and this was originally designed for our heat transfer class in chemical engineering, but we cover the same content as the mechanical engineering heat transfer class. And so ignore the fact that there's this pop-up menu. This is from messing with this for this class in past years, and I have added a pop-up menu that's not supposed to be there. So we defined some initial geometry that is a square, and it has dimensions of 1. For the purposes of an undergraduate class, they need to actually know what does alpha mean, and they need to be able to take into account some of the properties for numerical stability, and they can enter in temperatures. Here it's not even clear what units we mean, but that would be better designed GUI to have the units marked on the side, and it will calculate for us the Fourier number based on the properties that we enter above. It starts at the initial time step, and then we can propagate it through moving 3 delta t in each time we press the button. So we're moving just a few increments along evaluating the solution to this problem, and we'll always get where we get we can approach some steady state solution. We could put in more interesting heterogeneous boundary conditions. We start it again, and then it shows how it smooths it over time. And so that's what we started with. When in Monday's lecture, this is lecture 17, we will actually break apart this GUI and try to make it more user-friendly. But that's a heat transfer application. And the final one I'll preview, just go over, is our drug dosing app. We use this for a summer bridge program for our incoming freshmen in the College of Engineering, Architecture, and Technology for the chemical engineering design session. So trying to take some ideas from my research about pharmaceutical drug dosing and incorporate some key concepts that are taught in our undergraduate chemical engineering courses, but without having to have a lot of terminology with some of the big pieces of equipment and upper division class content knowledge. We wanted them to be able to do design, but not have to know a lot about chemistry and to not have to know a lot about reactors or equipment. And so we know that most people have taken some sort of medication, and so that's what was in mind in creating this simulator. And we gave fewer options, and we wanted to be able to do 2 different kidney function because that connects to our research. And 3 students over the course of the project, including Carly, who's in this class, read through the literature and found published data sets for humans with these 5 different drugs with normal and or impaired kidney function. So some of them don't have both scenarios, but they all have at least one, if not both of those kidney function, and basically took their data and put it in a table in the background, fit the parameters to the model, stored those parameters behind the scenes, and so when you click on these buttons, it actually will switch between data sets it's reading in. And we run it for either 1 day or 7 days so that you can see what a single dose does or what repeated doses do. There are boxes here that will give you text. So these are message boxes. We have some error messages built in. If you go over 20, this will send an error dialog box, and so that's a response that we want to have, that if this number is too high, this will open up and it will reset it back to the maximum value allowable. This one, the largest value is 24. And so again, it resets it to 24 rather than the 25 that I tried to type in. And this is why you don't want to give someone more than 24 doses per day. That would, I mean, you could, if you were giving a constant IV drip perhaps, but not for a pill that we're talking about as an oral dosage. So anyway, it's just kind of a silly upper bound that we incorporated here. We also thought that common behaviors that people would want to, ways they would want to interact with these plots would be to want to save them. So we made buttons for saving the top or bottom plots. We also figured they would want to be able to clear out the plots and start afresh, or they might want to be able to layer and compare two scenarios. So this is that same simulation, but let's say now we want to see what happens if we only gave one dose per day. What would that look like? It still reached the same peak, but then it started to go away. But it didn't have the same peak in the body, it had the same peak effect inside of the body. And so students could then use this comparison between different scenarios in order to make value judgments on what is a optimal design. We don't actually have an optimization algorithm on this. They're doing it by eye, but they're having to think about trade-offs. And so we knew what the purposes that we wanted to be able to explore. And so we put enough information in these captions so that students could see the different variables that they could compare from here on the input. They would be able to see those. We didn't put the number of days in the simulation because that's pretty well indicated here about how long it stays in the body. You can tell there's just one dose by looking at those. So we didn't have to put that in the legend. And you see, sometimes people will put lots and lots of things on here where if you keep running it, your legend will get quite crowded. And I'm just repeating the simulation in case you can't tell that I keep running the simulation. And so the legend will become quite large, so they might want to keep the same plot, reset it in order to clear out the legend and continue. It's cycling through the color order as well, and so that's something that we interact with on the back end to have it cycle through those colors again. And so that is our GUI. This one's a little bit larger because it has those data sets ingrained in the background. And we have made this one, we did a Journal of Open Source Software paper on it. And so we tried very carefully to have the code be very clear. There's just a lot of files with the code. So we have export fig as a package, and it has a lot of that is from others that have shared it on MATLAB on the online community, and so there's a number of M files associated with that. There's a number of map files that are associated with our data, but our main file is the GUI, one that starts with GUI. We also have the ability to run it without the GUI, and so we have some other scripts that basically run the model as it seems without the GUI so that we could probe other things for the purposes of plotting things in our paper, or to do them more quickly, or to allow users to change more variables. So we gave our users the option in our software paper to have this without GUI that's more appropriate for reproducible science, but then our novice users, our high school and incoming college student users, the GUI version. So we have, again, the normal kind of input stuff here. This one is reasonably long. It's not actually too bad for the actual, oh no, that's 600. I thought it was 69. Yeah, it's got lots of pieces in it. So we have a number of variables that need to get set up when it's initialized. And so basically these are all of the different options that are the default values in the parameters list. I have the wrong GUI open. It's these guys. It's what's stored in each of these boxes, essentially. What are these settings? If the user doesn't change anything when opened and clicks the Run Simulation button, that's the opening function would have set each of these values into the handles without having the user never interacted with it, so it couldn't be set during the callbacks. It had to be set during the opening. And so we use handles, the word handles, this structure, to pass around the key information in order for other functions to all run together. So I can't pass anything else. I can just pass around each object in handles. And so I got to make sure everything is stored in handles. So various calculated quantities, some are numerical, some are strings. When I am ready at the end of a function to save anything I update, I have to use this line, GUI data HObject handles. HObject says update using me, right? This is me, pointer to this current item. This is actually the whole GUI now. And then we don't really use event data. It says it's there for future use, and we're using the handles. So I'm going to update this current GUI with the handles. Right, so this last line is essentially save. Right, so at the end, it's a good practice at the end of any time you update anything with handles that you end that function with GUI data HObject handles. That is important. So this one actually says run the model and store some stuff about the plots. We want to restart the color order. We want to plot the baseline, so the solid red and black lines on there, just so that the user would know what the bounds are. Okay, we have a function. So this has some functions that are in here. These are ways that we are interfacing with the saved data. So if the user has specified a certain drug name, a certain renal function, this tells it which mat file to use. So this is gluing together different strings in order to read from a data file. So you might be able to read from a CSV file in a similar way, where you could use variables to glue together the name of something in a CSV file to read that in. And so this one is loading in very specific subsets of the stored values in this mat file in order to populate some of the constants needed for the simulation. There is actually running our model. So this is one of our user-defined functions that is in the current folder. And you don't need to worry about it, but it has a number of different inputs, and those are all values that were stored in handles. So handles.coefficient.t-final dosing. We say we want to calculate it for 24/7 no matter what. So 24 hours for 7 days, but we don't always show all of that time. This one also, we have the error messages. If the user selects the cases where there's no data, it will send them a message box that says that's not available, choose something else. And we created various functions that will allow us to plot things. We have two different plots, so we were very careful about giving those axes nicknames. So this might have originally been axis 1, but we said, what are we going to plot there? Drug versus time. So that is the tag for our top plot. And then we check some things. If the string that is stored in handles.drugName matches exactly this string, then we're doing drug number 1, 2, 3, 4. We could have done something else where we said, which row are we in? There's a number of different ways we could interface and determine which one was selected. We could use things with a pop-up menu in a different way. And it keeps going. It's doing some plotting things here. This is for the function that is update the GUI plot. Right, so it's saying which drug are we going to use, which values are going to read in, and putting the drug name in the legend. So this is really showing how we can use the dynamic legend to only, when we plot one thing, give it a display name, and then as we compose new lines into the legend, it will just update it as needed. So that's really helpful for holding on. We have a clear plots button. So we have a function that tells us what do we mean when we clear the plot. We don't want it to go away completely. We want to reset it to where it started at. So that's why we do the baseline and the 0. What does it mean to plot baseline? What does it mean to plot 0? These are internally user-defined functions. We have the internally defined function of what it does mean to clear the plots. The checkbox for layer plots is there, so we have just normal kinds of callbacks for how you interface with a checkbox. We don't have any output function from the GUI, and I haven't actually been able to make the output functions work, so I don't recommend using them. The run simulation is the most intricate callback because it runs that update GUI and it runs the model, but there was the separate codes that run the simulation and that update this. So we make the run button actually be, just a few lines long, but it's really the heart and soul of what's happening in this simulator. But because we know that we want to have the simulation run at opening and we want it to run when we press run simulation, we have made that a separate set of commands so that we've defined it as a function so that we don't have to copy and paste that text multiple times. Also, there's several different times when we might want to update the GUI. We might want to update it if we've cleared the plots, or we might want to update it with the solution if we have the starting values or if we are clicking the run simulation button. And so again, we have separated out those two different fairly lengthy sets of codes into encapsulating what they actually mean. And then we have a number of callbacks for what happens when we type in our editable boxes. And so dose size is one of those, and it has those limits of, well, if it's too big, too small, give those error messages. And then how to actually set the value we want and save it. We did have one thing in our create function where we set the initial value for that particular editable string. That's the only way we have used the create functions here. Okay, so there's a lot of boxes, so that's what all of that stuff is. The save bottom box, it says if you already have a file name of what you're expecting in your folder, it's going to beep and say, you already have this file name, I'm not going to overwrite it. So the user is prompted to move that or delete an existing figure file or PNG in this case, before overwriting it. And so that's something we added because we wanted the user to know if they were be active about saving that. There are very different ways to save the names of functions or save the names of files, and we did not use those more sophisticated techniques here because our target audience was people who we wanted to know what the name of the file was, basically, and so that we could control in that classroom setting everyone having the same name of a file so we could more easily help them. Now, for your own purposes and for the final assignment in this class, it's going to be better to be able to customize that based on what the user would like to do. Okay, goal. So these are the message boxes that happen when you press certain buttons about the drugs, about the goals. What are the drugs? And so this sets certain things based on which item is selected, 1, 2, 3, or 4, and some error messages, or 5. Function, very similar, gives some messages when those aren't available. Duration, setting some specific values. If it's the first one, we're going to set 24 hours. If it's the second one, we're going to set it to be 24 hours times 7 days. So that I know is a lot, but that is a really thorough working example, and so I think that is a lot of good sample code that you could use for a lot of different purposes, and so that's why I've gone so in depth about this particular one, and we're really proud of how we can use it, and we have polished it over time based on feedback from our users, and we like where it's at. So you in the class will get to play with some GUIs, get to design your own for a couple of different activities, but we're going to go into a better version of the 2D heat conduction in the next lecture, lecture 17.